Okay, so here's an example. Example 6.5.12 in my notes, and let's see if we can look at this one right quick. Let me zoom in a bit. Alright, so we're asked to integrate this rather unpleasant function of the square root of 4 minus x squared minus y squared over this region, x squared plus y squared less than or equal to 4 and x greater than or equal to 0. So that's this region right here, right? Which is actually pretty easy to describe in polar coordinates, right? It's 0 less than or equal to r less than or equal to 2. And it's convenient to use negative angles for this one. So like minus pi over 2 less than or equal to theta less than or equal to pi over 2. Now the reason you want to do that is because if you used angles from 0 to pi over 2 and then from 3 pi over 2 to 2 pi, you'd have to break up the integral into two pieces, which would just be silly. So so thankfully we're always able to do that kind of adjustment now. And so the way we do the integral then is it's very very natural. The bounds for that half circle, half disk rather, are simply minus pi over 2 to pi over 2 for theta and 0 to 2 for r, right? And now I put x equals to r cosine theta and y equals to r sine theta, but I mean honestly folks, you could just look at it and go, okay, so 4 minus x squared minus y squared is really just 4 minus r squared, right? And then remember the key thing that we have learned from the way to understand the change of variables theorem is that dA is r d theta dr. That's essentially half of the change of variables theorem. The other half is you got to change the bounds. Well, we change the bounds, and we put in the dA as r dr d theta, or r d theta dr in this case, appropriate to the bounds, and now we can integrate. So the theta integral just gives us a pi, and then the r integral can be done with a u equals 4 minus r squared substitution. I think something happened here typo-wise. 4 minus r squared to the 3/2 u. Yeah, so I think, sorry, every so often here there's some unfortunate typo in the notes. I'm glad I'm working through this with you. So that's just not there at all. But we evaluate from 0 to 2. I do think that that's the correct integrand, antiderivative rather, for that expression. Yeah. And so when you plug in 2, you get 0. But when you plug in 0, you get the 3/2 root of 2, which is 2 squared to the 3/2, which is also known as 2 to the 3, which is 8. So we get minus 8 pi over 3. And there you have it. Now, of course, this integral would have been much, much nastier if we had done it directly in Cartesian variables. We would have done something like integral from, 0 to 1, integral from the square root of, let's see here, it's a circle, so 4 minus x squared to the square root of 4 minus x squared, that would be my y bounds, square root of 4 minus x squared minus y squared dy dx. So which one do you want to do? Do you want to do this, or do you want to do that? I mean, I know which one I want to do. So polar coordinates are really important for making the integration of certain integrals just go much, much better. Here's another example. Here we have r as the region in the xy plane with 1 less than r less than 2 and 0 between theta between, so it's like pi over 3, and that's theta, and theta equals to 0 is the lower bound, and r goes from 1 all the way out to 2, so this is like a sector. That's a picture of r like that, yeah. and we're doing that integral of 1 over the square root of x squared plus y squared. So in polar coordinates, that's 1 over r. dA is r dr d theta, and the r's cancel, and we can just do that integral and get pi over 3. That wasn't too bad. All right. This example is just me messing around, and but the point of this is you could calculate the area of a triangle using polar coordinates. So if you want to, so this also introduces maybe our first example where the r integral is set up with a, basically you've got r in less than or equal to r less than or equal to r out. So more generally, these guys can be functions of theta. Is possible. I think the examples I've had up till now, we've been looking at sectors, so the radius have not been functions of theta. They just, like the last one went from 1 to 2, but this one, the inner radius is 0, and the outer radius is given by that line, x plus y equal to 1, which has the rather unpleasant polar formulation of 1 over cosine theta plus sine theta. So to calculate the area of the triangle, I integrate dA, all right, and dA, of course, is r dr d theta, but I also have to change the bounds, and so the bounds in polar coordinates go from 0 to that r out, and 0 to pi over 2, right? Notice that this triangle, now that may be less obvious to you, but this down here is theta equals to 0. And this up here is theta equals to pi over 2. So as I think about polar coordinates, I've got 0 less than or equal to theta less than or equal to pi over 2 for the theta bounds on that problem. And so great, if I make good on this problem here and do the integral, well then I've got, r dr d theta integrated like that, so the r integrates to r squared over 2, which gives you this. And hey, that's cosecant of theta plus pi over 4, because you notice the cosine theta plus sine theta, by the way, fun fact, that's sine of theta plus pi over 4. Everybody knows that, right? So when you have the square of the reciprocal, of this, that's the cosecant, and the integral of cosecant squared is minus cotangent, and so yeah. There you go. Area of a triangle with a base and a height of both 1 is 1/2. Yeah. So is this the right way to do this problem? Absolutely not, right? Because this problem is not something that really involves circles, or even, I guess it sort of involves rays, but certainly this problem is much more natural in Cartesian terms. So here's another example. I have the region r equals to 9x squared plus 4y squared less than or equal to 36. And just to recast that a bit, that's, another way to look at that would be x squared over 4 plus y squared over 9 less than or equal to 1. You might recognize that as the equation of an ellipse at the equality, and thus what we're really looking at here is an elliptical region that goes from plus or minus 3 in the sense of y to plus or minus 2 in the sense of x. So it's an ellipse like this. We're integrating over this elliptical region. That's what's going on here in this problem. This is the quote-unquote r, right? And what I describe in this example here is that we can use x equal to 2u and y equals to 3v to convert this into 36u squared plus 36v squared equals to 36, which is to say u squared plus v squared equals to 1. So I transform the ellipse into a circle in uv space, calculate the Jacobian as being 6, And so if I'm going to integrate x squared over this ellipse, I can integrate 2u squared times the Jacobian of 6, which gives me 4 times 6 is 24, 24u squared du dv. But I would, great, but here s is in the UV space, all right, and it is a unit circle. So again, I don't really want to do that integral in u and v either, because it's still ugly. It's a circle, it's a disk rather. And so if we introduce polar coordinates in UV space, right, make a second change of variables, right, u equals to r cosine theta, v equals to r sine theta, then the space transforms from a circle into the 0, 1 Cartesian product with 0 to 2 pi in our theta space, and so I can change the integral, change the bounds, 0 to 2 pi for the theta, 0 to 1 for the r, and u squared gives me r squared cosine squared theta, du dv is r d theta, 24 is 24, and so I end up with this integral, and I can work it out. I get 6 pi. So that's a pretty good example. There's a lot going on in this example. I like it. The next example is pretty much like ones I've already looked at here, so I'm going to go on. And this one's a little bit more interesting. So here we have the integral of inverse tangent of y over x, right? And this region here is r squared is going between 1 and 4, and y is between 0 and x, right? So a picture of that is you're on this annulus, right? The inner radius is 1, right? Because this is 1 less than or equal to r squared less than or equal to 4. So that says 1 less than or equal to r less than or equal to 2. That's how the r is varying. And then you're going from theta equals to 0 there, right? That's theta equals to 0. And y equals to x, well, that's theta equals to pi over 4. So we're integrating from an inverse tangent of y over x, well, that's just theta. So we're integrating theta r, and the r from, again, dA is r dr d theta, right? That's the change of variables theorem in action. And again, the other action is changing the bounds. So 1 to 2, 0 to pi over 4, theta r dr d theta, and you go through the steps, and you get 3 pi squared over 64. So it's pretty good. Aha! Now finally, going back to a question about volume. So the next example here is about volume. So supposed to find the volume bounded by 18 minus 2x squared minus xy squared and z equals to 0. Ooh, I wonder if there's a typo right there. Yeah, that's supposed to be that x right there. There got lost in translation from my notes. I think that is a 2. That is definitely a 2, because if once you make that a 2, then you can see what you have is z is equal to 18 minus 2 times parentheses x squared plus y squared. So in polar coordinates, you've got 18 minus 2r squared. Now that looks like something that would be natural to make a polar coordinate change. So the double integral will yield the volume, right? So we're going to integrate z dA to get the volume, the sine volume. I guess I'm assuming here that z is positive in the region of interest. Let's see here. Oh, I see what I'm doing. I'm supposing z equals to 0. Oh, the z equals 0 is the other bound, right? So what this is actually one of these guys. Right, so like the zenith is at z equals to 18. And then down here in the xy plane, you know, this is z equal to 0 down here. And this calculation, setting z equal to 0, gives you 18 is equal to 2r squared, or r squared is equal to 9, so r is equal to plus or minus 3, but we insist r is positive here. So the equation at circle is just r equals to 3. All right, and great. So in terms of polar coordinates, then we have well, we go all the way around, right? 0 to 2 pi, and from 0 to 3 for r. But what about? So I think I'm actually. Okay, yeah, that's fine. Fine. I was thinking about cylindrical coordinates here, but there's no need. This is a double integral. So all right. So the integral of z dA, changed to polar coordinates, r d theta. Z is 18 minus 2r squared, and r goes from 0 to 3, and theta goes from 0 to 2 pi. And so there you go. Yeah, 81 pi. All right. Now, let's see here, this one. Volume bounded by z equals square root of x squared plus y squared and the sphere, unit sphere. All right. So that's a cone bounded by a sphere. It's the upper cone, not a double cone. Z is positive here, or not negative at least. Let's say I said the equations are symmetric in x and y, so we can denote that, I mean, we can deduce that 0 less than theta less than 2 pi. And the intersection of these two surfaces has 2r squared equal to 1. I think that's clear, because if I plug in z squared, I get x squared plus y squared plus x squared plus y squared equal to 1. In other words, 2r squared equals to 1. So r is equal to 1 over root 2 on the intersection. So we've got 0 less than r less than 1 over root 2. And, yeah. So let's see here. I'm finding the volume in terms of the top z minus the bottom z integrated over a. It's like a typical infinitesimal volume. And so that ends up being square root of 1 minus r squared minus r dr d theta, and then I integrate that like so, and get that. So great. Now the other way to do this would have just been like another way to think about this problem, it might even be better perhaps, would just to have said, well, the integral, triple integral over dv gives you the volume, right? Let me see where I can write here. Oh, there we go. Okay, it gives you the volume. And so that I could integrate from 0 to 2 pi for my theta, from 0 to what's r? R goes from what? From 0 to 1 over root 2 for the r. And then the z is interesting. The z bound is variable. Z goes from the up from the cone. The cone has z equals to r, and the sphere has z equals to the square root of 1 minus r squared. And I can choose the plus because we're in the upper half of the sphere in the intersection. So 1 minus r squared that's the z upper, z lower. And then integrate dv. Well, dv in cylindrical coordinates is actually r, and I got to write dz, dr, d theta. And so if you do this integral, it works out the same. But that's how I would actually think about this volume problem. I would think about it in terms of cylindrical coordinates and integrating dv. So, but I guess technically I'm out of order here because I haven't talked about the cylindrical volume element yet. Let me kind of get on with it here and go on to that material. I have a few more examples, I think, in polar coordinates. Excuse me. Let's see here. This one, yeah, it's yet another polar coordinate example. This example here is actually very interesting and a standard thing you should see. We can calculate the integral of e to the minus x squared minus y squared dA over the whole plane in this limiting way. We can say, okay, so that's really, e to the minus r squared, and take the limit as the radius goes to infinity, 0 to 2 pi, and by u substitution, that's e to the minus r squared. E to the minus r squared, evaluating from 0 to a, we get e to the minus a squared plus 1. Of course, that drops to 0, and we're just left with pi. So the integral of that function over the whole plane, with this interpretation of integral of over whole plane, this natural interpretation rather, is pi. And on the flip side of things, we could also calculate the integral of e to the x squared minus y squared as, as this, where a is the cube, well, the square rather, from minus a to a, from minus a to a, right? As a goes to infinity. That's the other way we could look at it. And if you think about that, you can calculate that integral by integrating minus a to a, and this by algebra is that. And so these don't have anything to do with each other, so you can write it as a product of the integrals. And so you might as well write the limit on both of them rather than one of them. And great, so you got this integral squared, and so lo and behold, you've proved that the integral from minus infinity to infinity, essentially, of e to the minus x squared dx is equal to the square root of pi. Assuming that the principal value actually is the integral, but yes. So that's kind of cool. Now, if you'd like to see a lot more that you can do with this, I would highly encourage you to look at Keith Conrad's differentiating on the integral side. He is what he calls a blurb. So his blurbs, super useful. He has a website, Keith Conrad. Look him up. Incredibly useful writing, typically at a very high undergraduate or very low graduate student level, but sometimes research level. Anyway, super useful. Look it up. All right. So that brings us to triple integrals. All right. And so for triple integrals, the Jacobian is a 3 by 3 determinant. The determinant of this 3 by 3 matrix. And just to get to the point, when you calculate the Jacobian for cylindrical coordinates, you get r, which basically means for me that dv is equal to, well, dx dy dz, but it's also equal to r dr d theta dz, which kind of makes a lot of sense because this dx dy we have previously interpreted as r dr d theta in the polar coordinates, right? And then this one is less easy, but spherical coordinates, rho cosine phi, cosine theta sine phi, rho sine theta sine phi, z is rho cosine phi. Well, if you calculate the Jacobian of this monstrosity, and you use sine squared plus cosine squared being 1, well, I got minus rho squared sine phi because I did rho theta phi. But if you had instead calculated partial x, y, z, partial rho phi theta, so I got to put the phi first and the theta second, then this would work out to rho squared sine phi. And so that goes to show you that dv you could also write as rho squared sine phi d phi, d rho, d phi, d theta. So this is the volume element in spherical coordinates, and again, that's half of the change of variables theorem. Here's the the volume element in cylindrical coordinates. All right, and so, and here's another example: Jacobian 3 by 3, and another. All right, great. But here's the change of variables theorem, right? We take our function of 3 variables, we rewrite it in terms of the new variables u, v, w. We multiply by the Jacobian of x, y, z with respect to u, v, w, and then, of course, also change the bounds from the Cartesian description to the u, v, w description, and that's how you go. So, in particular, for cylindrical change of variables, we take x and replace it with r cosine theta. We take y, replace it with r sine theta. And z is z, and we change dv to r d theta dz. That's how you do the cylindrical integral. Spherical change of variables, in contrast, you trade out x for rho cosine theta sine phi, and you trade out y for rho sine phi sine theta. You trade out z for rho cosine phi, and your dv is rho squared sine phi d phi d theta d phi d theta d rho, or d. I mean, these go in order as appropriate. So here's an example. Integrate x cubed plus xy squared. All right, let me get this out of the way here. Integrate x cubed plus xy squared dv, where e is the solid in the first octant, which lies beneath the paraboloid. Z is equal to 1 minus x squared. All right, so this actually suggests this is not a spherical one. This suggests a cylindrical approach because basically z is above and below. Well, it's in the first octant, which means z is greater than or equal to 0. And the top z is 1 minus r squared. So it goes all the way around. So we're going to use 0 to 2 pi for theta. And, oh, wait a minute, first octant, right? So, my bad. First octant, theta doesn't go all the way around, it's up in here. It's where first octant is where x, y, and z are all positive, or rather non-negative. So that means 0 less than or equal to theta less than or equal to pi over 2 up in there, right? Because theta equals to 0 is basically this half plane, and theta equals to pi over 2 is that half plane. I say half plane because it goes up and down also, right? Anyway, so theta equal to a constant is a half plane in cylindrical coordinates. But anyway, here we go. So we integrate this bad boy here. So my z goes from 0 to 1 minus r squared. My r goes from 0 to 1 because that's the biggest it gets. When I put z equals to 0, I get that z equal to 0 brings me to r squared equals to 1, so r is 1. And again, the theta goes from 0 to 2 pi, so I integrate like that and do the integration, and I get 1/12. Great. This next one screams spherical coordinates at you. Consider this integral of exponential of the square root of x squared plus y squared plus z squared over x squared. So this is e to the square root of rho over rho squared in spherical coordinates, right? This is exactly e to the rho divided by rho squared if you put it into spherical coordinates, right? And the integration region is nothing more than 1 less than or equal to rho squared less than or equal to 9. So, and there's no, so that means we're going to integrate over the whole range of spherical angles, and yeah. So 1 less than rho less than 3, and 1 less than rho less than 3, and here we go, e to the blah over blah squared dx dy dz. So we go 0 to pi for phi, we go 0 to 2 pi for theta, and we go 1 to 3 for rho. And 1 over rho squared e to the rho, that's f. And then again, dx dy dz is rho squared sine phi blah blah blah, d rho d theta d phi. So the rho squareds cancel, which is super nice, and you're just left with, well, e to the rho sine phi and well, d theta. So since there's no intertwangling of the functions, you can just multiply the integral of phi times the integral of theta times the integral of rho, keeping the explicit dependence with each integral, so sine phi. And so like integral of sine phi d phi from 0 to pi is 2. This gives me 2 pi, and this gives me e to the 3 minus e to the 1, so the answer is 4 pi e cubed minus e. Yep. Yep, yep. And so I have more examples. Find the center of mass for the region which is above the cone. Z equals to z equals square root of x squared plus y squared, and below the sphere x squared plus y squared plus z squared equal to 1, and we're going to assume that E has a constant density delta. So to find the center of mass, you take the total mass weighted average of x, y, z over the given solid. So by definition, that means you have to do 3 triple integrals, actually 4, because you got to do another integral which figures out the mass. But anyway, so 1 over mass integral of x delta, 1 over mass integral of y delta, 1 over mass integral of z delta over the volume gives us the x, y, and z coordinates of the center of mass. And of course the m, the total mass, we get from integrating delta dv. So in all 4 of these integrals, spherical coordinate choice is convenient. Here's the picture of the solid. Picture of the solid right here. So basically theta goes all the way around. Rho goes from 0 up to 1. And phi goes from 0 at the top. Phi 0 is up here, and down here that's phi equals pi over 4. That's a pi over 4 in there. You may or may not be able to read it. Alright, so those are the integrals. That's the bounds, the spherical description of the bounds we got to do. And so to start with, I'll calculate the mass. So we have to integrate delta times, well, the volume element, and it gets us 2 pi delta over 3 times 1 minus 1 over 2 when we do the integral. And on the other hand, by the symmetry of this problem, you can see that the x and the y center of mass are 0, right? So we don't actually need to do these integrals. We don't actually need to do, because the integral of x and the integral of y over this volume will be 0, because x and y symmetrically are both positive and negative as we consider the entirety of that volume. Z, on the other hand, there's an asymmetry in the z, and we expect that the z center of mass is somewhere right about there. I don't know. Got to do the integral. So since delta is a constant density, we can get that the volume is, I don't care about the volume, whatever. Let me go on here. Z center mass. So the z center of mass, 1 over m integral of z delta dv, and once more we face the same bounds in sphericals. This time I put z, see that z is equal to rho cosine phi. dv is once again rho squared sine phi, d phi d rho d theta. And again, I can uncouple the integrals and just multiply them because they've got nice, boring constant bounds. I get delta over m, theta evaluated from 0 to 2 pi, and the rho integrates to rho to the 4th over 4, 0 to 1, and I've got sine phi cosine phi, so that integrates to sine squared theta over sine squared phi over 2, and so lo and behold, we get delta m times pi over 4 for my z center of mass. And great, so that means that 0, 0, pi delta over 4m, that's the center of mass. But we can do better, right? Because the mass is given as, I mean, I have mass over delta up here is that, right? So we can use that to get rid of the delta and the m and write it as a pure number, probably on the next page of my notes. Yeah. Here we go. So center of mass for that cone is 0, 0, comma 3 root 2 over 8 times square root of 2 minus 1. So there you go. Now in this problem, we just calculated the center of mass, but that's the same as the centroid. The centroid is the geometric center, and it can always be found by assuming the density is 1. So again, centroid or geometric center assumes uniform mass density is one way of looking at it. All right, but for a mass for a solid where the density was not constant, there could be a distinction between the centroid and the center of mass. Now this example is near and dear to me. This is in physics another thing we need triple integration to study is something called the the moment of inertia. And so to calculate moment of inertia with respect to the z-axis, what you do is you have to integrate the density times x squared plus y squared. In other words, the density times the distance from that axis squared. This gives us the moment of inertia about the z-axis. And if you do that for a sphere, you get this integration. So notice that the integration goes from 0 to r, 0 to pi, 0 to 2 pi. These bounds give you like the full sphere of the integral. And you end up with, after you work it out here, 2/5 mr squared. So there you go. That's the center, that's the moment of inertia for a sphere. And now if you had a course in physics, this result was probably told to you, but it's very doubtful it was derived for you, because to derive moments of inertias for three-dimensional solids, you really need calculus 3. Which is why a lot of physics professors might say to you that you should really have calculus 3 before you take physics 1. A viewpoint which I agree with, but people who want lots of students in classes and, the bottom line, money, 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 will disagree with. Anyway, it takes a while to get through calculus 3, right? People want students in physics 1 before they get through calculus 3, unfortunately. So we just have to give you some things in physics 1 that aren't derived, right? But here's the derivation. And well, here's a fun calculation. This is the kinetic energy for a rolling sphere, a sphere rolling without slipping. It's got both a kinetic term, a linear translational term, and a rolling rotational term. Anyway, so I shut up about that. Really don't have much more to say about that. That's physics. Now, the next example is a nice example. This is the analog of the ellipse problem we had earlier. This one is over an ellipsoid. If you face an integral over ellipsoid, it's usually a good idea to make a change of variables, like u equals to x equals to au, y equals to bv, z equals to cw, so that it changes the ellipsoid into the unit sphere. And once you have a unit sphere, then life is easier. So this one, because I don't think I ever quite wrote it out here, but oh, I have it right here. Come on. So see right here? If you take partial derivatives, you can see that. We get a 0, 0, 0b 0, 0, 0c. So the Jacobian of this change of variables is just ABC. It's kind of cool. And of course, B is actually the unit sphere. So what's the volume of a unit sphere? Well, it's 4/3 pi. Oh, something we haven't done in here yet is calculate the volume of a sphere, right? That's easy enough to do. Volume of a sphere. Let's calculate it. So we integrate from 0 to 2 pi. integrate from 0 to pi, integrate from 0 to r, we'll do r, and then the spherical volume element, rho squared sine phi, d rho, d phi, d theta. Alright? So since there's no dependence, I can do the theta integral first. I can do the phi integral second. Just got to put all my phi stuff together. And I can do my rho integral over here. That's lonesome. And when I do that, I get 2 pi. This integrates to 2. And that integrates to r cubed over 3. And that's the reason that the volume of a sphere is 4/3 pi r cubed. That's a result that we should know. And more than just know, now we can derive it. It's easy to derive with spherical coordinates. And so anyway, since that's a unit sphere, it has volumes 4/3 pi, which gives me 4 pi abc over 3. And of course another way to look at this is now you can derive the volume of a sphere by saying a equals b equals c equals r, right? Because an ellipsoid is a sphere in the case that all the ABCs are equal. Alright, but anyway. So, yeah, oh, and here, so I've calculated the volume of the unit sphere here. Look, I've gone through the spherical Jacobian yet again. Right, we did that earlier in the notes, but I'm regurgitating it once more. And, yeah. Oh. So, let's see here. Next up, I have a integral over a cylinder. It's a nice example. Past that, I have a cylindrical coordinate integration. All right. This one here, I find the mass of a ball such that the ball has radius a, and oh, this one actually has a non-constant density. So I have a density proportional to the radius. So it's like it's most dense at the edge, and it has density 0 at the center. And so like that one, the reason this is in the notes is just to illustrate that you can calculate mass of non-constant densities with triple integrals, right? So here's how that goes. And I changed the sphere to cylindrical coordinates here because the integrand was given in terms of kr. So this is kind of an interesting example because it shows you this is how to describe, right? The interesting thing, this example should be noticed because it can be useful to you if you ever come across a problem where you have to take a problem with spherical bounds and describe them in terms of cylindrical coordinates. This is the description of a sphere in cylindrical coordinates. All right, and it's a little bit tricky, right? So there it is. And great, so I use those bounds to integrate rho dv to get the mass, and it's still nasty. Oh man. So then I had to make a trig substitution, which I felt obligated to explain using imaginary exponentials. And after some some work, I got k pi squared a to the 4th over 4. Whoa. That's a tough one. That's a tough one. All right. Now, it turns out that that previous example would have been probably easier if I just, instead of going to the trouble of changing the bounds to of the sphere to cylindrical coordinates, if I'd instead just taken my medicine and said, okay, so rho equals to kr, I can rewrite as, oh goodness, this is the density. So I shouldn't use rho, I should delta equal to kr, density. Sorry, in physics we use rho for density. My apologies, it still hasn't worn off. So delta is equal to kr, which is k rho, rho sine phi. Right, because remember this picture? If we think about this, here's our z, this is phi, this is rho. So that means that this down here is rho sine phi. But it's also equal to the r, the distance from the z-axis. So yeah, r is equal to rho sine phi. If you want to convert cylindrical radius to a spherical formula, that's how you do it. And that's how we should have done this problem rather than the way I did in the last, because man, it's way easier to integrate with the spherical bounds. Yeah, I mean, the formula's a little bit unpleasant, but man, it's so much easier than the way I did it. Yeah, moral of the story, coordinate choice matters. I agree. I agree. All right, and another example. I'm sorry, I'm worn out here. Oh my goodness, is there any end to these examples? Good night. Oh yeah. So yes, I have examples after examples after examples. Oh. This one's it. Actually, this one's useful. So this one starts with Cartesian coordinates, and I change it to cylindrical coordinates. So -3 less than x less than 3, and y goes from that to that, right? And z goes from that to that. And so if you kind of unravel all this, we're actually on a half circle of radius 3, and z is bounded below by 0 and above by 9 minus r squared. So that rather ugly integral up here can be traded for this cylindrical integral, and it's 162 pi over 5. Alright, and this finally brings us to almost to the end, which is we can also do integration in n variables, and the change of variables, pretty much the same song and dance. You convert the formula for the integrand in terms of the new variables, multiply by the determinant of the Jacobian. This is now the determinant of an n by n matrix of derivatives. And just to give you a flavor, if you wanted to calculate the volume of a hypersphere, in other words, x squared plus y squared plus z squared plus w squared less than or equal to r squared, you could introduce generalized spherical coordinates. So you got a phi and also a psi, and you can check that when you add x squared plus y squared plus z squared plus w squared, this works out to little r squared, because you get this like stacking of sine squared plus cosine squared. And so in this wild new four-dimensional world, you'd have theta going from 0 to 2 pi, and you'd have both phi and psi going from 0 to pi to describe the four-dimensional volume, or hypervolume as people say. And it's a long, straightforward, but tedious calculation that the Jacobian of x, y, z, w with respect to r theta phi psi is in fact r cubed sine squared phi sine theta, sine phi rather. And consequently, if we calculate the four volume in generalized spherical coordinates, we'd integrate this bad boy here, and if you work it out, you get pi squared r to the 4th over 2, which is kind of cool, I suppose. So, yep. So I actually use this result to calculate Gauss's law in 4 spatial dimensions in my Math 430 notes. Maybe I'll do that in here at the very end. I'll show you. And here's a couple of more examples in 4 dimensions just for kicks. So I don't think I have any 4-dimensional problems for you, but what we're doing, it equally well extends to higher dimensions. So anyway, I'll stop here. Sorry for having so many examples and not talking faster. I hope you see that really it's a lot of the same. What we have to do is we have to understand the bounds carefully, And if we're going to make a change of variables, we have to also change the measure, the dV or the dA, either to rdr d theta for polars, or to rdr d theta dz for cylindricals, or to rho squared sine phi d rho d phi d theta for sphericals. And then more generally, we have to use the Jacobian factor for other more inventive changes of variables, as we've seen. So thanks, guys. Sorry this went so long.